We check. I send you as references. I sent him differentiation. I decided that's why I got no idea. Okay, so welcome everyone. I think we'll get going. My name's Stefan Luene-Smith. I'm the chair of the Department of Mechanical and Aerospace Engineering. I'd like to welcome you to the Penna Lecture, Penna Memorial Lecture, which is happening, and this is spring. We have one every quarter. This is a series established by the founding chair of what was then the Ames Department, Sol Penna. And so these invite distinguished speakers to talk about areas of interest to the general mechanical and aerospace engineering community. So thank you for coming. Delighted to welcome today Professor Juan J. Alonso from Stanford University, the Department of Aeronautics and Astronautics, and I'm going to pass the baton over to John Huang to give a slightly longer introduction.
Okay. Thank you, Stefan. It's a real pleasure and honor to introduce Professor Juan Alonso for our spring panel lecture. On a personal note, this introduction is especially meaningful to me because my PhD advisor, PhD and postdoctoral advisor, was Joaquin Martins at Michigan, whose own PhD advisor was Professor Alonso. So in academic parlance, that makes Professor Alonso my academic grandfather, and a very young academic grandfather. So a lot of the good so a lot of I think the ways of thinking and values that really shaped my own training in multidisciplinary design optimization really traces back to Professor Alonso. So really it's a treat to have him here. For those of you who don't know, who don't work in aerospace, I want to give a brief introduction for our speaker. So Juan Alonso is the Vance D. and Arlene C. Kaufman Professor of Aeronautics and Astronautics at Stanford, where he chairs the Aero-Astro department. He also directs the Aerospace Design Laboratory. He has authored over 300 technical publications, and his group developed SU2, which is one of the world's most widely used open source suites for CFD, multi-physics simulation, and design optimization. Beyond Stanford, Juan has served as the director of NASA's Fundamental Aeronautics Program in the late 2010s, where he oversaw the agency's entire aerospace vehicle research portfolio. He has helped shape U.S. and international aviation policy through rules on advisory bodies for NASA, the FAA, and the ICAO, the International Civil Aviation Organization. He's also co-founder and CTO of Luminary Cloud, which is a well-funded startup rethinking high-fidelity physics simulation through GPUs and cloud computing. Some of the partners, including NVIDIA, Northrop Grumman, and Joby Aviation. His awards include the NASA Exceptional Public Service Medal, the NASA ARMD Associate Administrator Award, multiple AIAA Best Paper Awards, and the AIAA Stanford Chapter Professor of the Year Award, which is awarded by the students, and he's won 8 times. Professor Alonso today will tell us about a multi-year study where data from more than 200,000 flight trajectories in and around SFO were used to evaluate how accurately the FAA's regulatory aircraft noise prediction tool captures measured aircraft noise. And this is a topic with very real consequences for US aviation policy. And it's also a great example of this work that you're about to hear about how large-scale data can improve and validate our physics-based models. Please join me in welcoming Professor Alonso.
Well, thank you very much for the introduction, gentlemen, and thank you for having me today. I mean, it's a real pleasure to come to UCSD and to speak to an audience of both, I know, aerospace and mechanical engineers. So, when you told me this was the Penner lecture, I did a little bit of research, and I found that there's more commonality between your department and my department than I thought. Turns out you were started in 1964. The Department of Aeronautics and Astronautics at Stanford was started in 1958, 59. Does anybody know what happened in 58 that may have spurred many of these departments to start around the nation? So, yes, so for the younger the youngest in the audience, Sputnik flew. And this was an eye-opening experience to the point that many graduate-only departments, that's the second thing we have in common. Our department started as a graduate-only department, masters and PhDs. Well, these departments were requested by industry to be funded in order to support sort of the burgeoning field of aerospace engineering. And of course, with a strong geopolitical imperative like the ones that we have going on today. And the last thing I said, Professor Penner, which I guess went by Saul Penner. I don't know if any of you met him. I did not. If you notice, his first name is not Saul, it's Stanford. so anyway, thank you for having me today. I'm going to actually talk about a topic that has relatively little to do with most of the research that I do, and that John sort of mentioned that it's mostly related to design optimization of aerospace vehicles. But this is a project that came completely accidentally. So the FAA occasionally reroutes aircraft traffic around various different areas. With the advent of GPS, I'll show you some pictures in a moment. What ends up happening is that the aircraft end up lining up like little ants inside, into and outside of airports. So you have all of a sudden very concentrated paths of aircraft that are flying or overflying people 300 times a day. And of course, anytime the FAA does this, there are lawsuits galore. Everybody tries to stop this from happening, so on and so forth. So this happened in about 2016 around Palo Alto, which is where Stanford University is. And I was asked to go to the Palo Alto City Council to answer questions about aircraft noise and various other things. I don't know why they thought I had any idea what aircraft noise was, but I answered many questions, and they asked me to sort of advise them on what they could do, what studies they could conduct. And at that meeting, I met a former Stanford physics professor and a software developer in the area. And the three of us decided that there was not enough data to actually understand what's the right thing to do. So we were going to develop a system, pro bono, to just look at data collection and data analysis for the city of Palo Alto. So for 2 years, we worked on this. The FAA caught wind of it and said, well, you guys are putting together a system that's going to collect more data than anybody has collected in this topic. So let us fund you to continue that project. And we've been doing that with FAA funding for about 4 years now. So I'm going to present to you the results of a journal paper that we published 1.5 years ago. That is kind of the first large-scale study of an assessment of the noise related to aircraft in the Bay Area and the accuracy of the tools that are today used for regulatory purposes in the US and abroad, which are, TLDR, as the youngsters will say. They're not very good at all. In fact, that needs to significantly improve. So anyway, I structured the talk so I can maybe talk a little bit about introductory topics, knowing that not everybody here is an aerospace engineer. and maybe this is the first time you hear about noise. So, I'd like to start by saying that in general, the aviation enterprise is an amazing thing. Being able to fly at almost the speed of sound anywhere in the world, and let's say 10, 12 hours maximum, et cetera, et cetera. It's just fabulous. We have to continuously improve the efficiency of that system, just like we do for any other means of transportation. But in particular, people like me, worry about the sustainability of that aviation enterprise. So both efficiency, but also the detrimental impacts of actually having the service that we call aviation. So obviously, you have an airplane that flies at a certain altitude, it burns fuel, it sucks in air from the front, and things like CO2, water vapor, and then a whole bunch of other things get produced. Those are obviously environmental impacts. In fact, all of those gases that are the exhaust products of the engines get mixed with the atmosphere. And the atmosphere is like a big vat of air where these things get put in, and it's just mixed around by some currents, weather patterns, so on and so forth, right? But I'm not going to talk very much about that. Of course, to produce the fuels, you have some significant sort of environmental impacts to run the airports and the infrastructure. You have to do all those things. All of these things do change the climate, obviously. And some of the pollutants have environmental impact in terms of health impacts. I'm not going to talk about any of those environmental impacts of aviation, although they're all very important. What I'm going to talk about is the fact that aircraft, particularly at low altitudes, when they operate in and out of airports, end up having an impact on the overflown population that is related to the nose that they actually produce. So that's what I'm going to focus on today. But environmental impact of aviation is a very broad topic. So let me actually say that this is a little tongue-in-cheek, but the environmental challenges of aviation are not new. So in 2023, we celebrated the 120th anniversary of the Wright brothers' first flight, as you all may know. So Kitty Hawk, fewer than 100 meters in distance, right? And now we're flying all over the lot. It also there was the 112th anniversary of the first editorial complaining about aircraft noise. So Aero magazine, which is the precursor of Aviation Week in Space Technology, so the preeminent magazine in the aerospace industry, said, or had an editorial that said that the tremendous racket that is present associated with the aeroplane plays a considerable part in prejudicing the public against these machines. And you could say that today. It has not changed, right? Of course, the noise sources are different, the volume of aircraft is much different, but this is something that generates a lot of negative reaction on people who hear these airplane noises. People like us who love airplanes, we think that's the sound of freedom, as people say, so I don't want to disturb. But the reason I'm in this thing is because my wife doesn't like it, and she forced me to work with the city of in some senses. So I do want to sort of introduce noise from aircraft in particular. So predicting noise is actually pretty hard. So I don't know if you can you see that more or less? That says San Francisco up here. So you can see it right there. Palo Alto, that's where we are. So this body of fluid is the San Francisco Bay. This is the Pacific Ocean, et cetera, et cetera. And I just want to sort of impress upon you how difficult it is to predict the noise of many aircraft flying around in a 24-hour period. So typically we start with a bunch of elements. So we have a bunch of airports, the white dots in the area, and 3 major international airports in the Bay Area: San Francisco SFO, Oakland OAK, and San Jose SJC, right? Not only that, but the way we organize traffic in and out of those 3 major international airports is through these waypoints, those little green dots. I'm sorry if you can't see there, that you can see over here, right? That ends up on a 24-hour period, colored by altitude of the aircraft, resulting in that mess of trajectories. So every 24-hour period, we're collecting this data, as you'll see later on, but that's what happens. So every one of those paths, and I'm going to animate it in a moment because it's almost impossible to make sense out of this. Every one of those paths represents an aircraft overflying, and the magenta colors are low altitudes. You can see the approach to SFO and the departures. The blue colors are very high altitude. So there are aircraft that transit at 30,000 feet above the Bay Area, which have no noise impact whatsoever, right? So look down here. This is Thursday the 13th, 3 a.m., 6 a.m., 9 a.m., 12, all the way. This is a 24-hour period. That's a histogram of how many flights are there in the air within a 250-mile radius of the Stanford Hoover Tower, so our campus. And I'm animating these things. So I'm going to click go, and you're going to see effectively a 24-hour period, starting very early in the morning with a very few flights, to the aircraft arriving from the East Coast, you know, at around 6, 7 a.m. or so, and then departure, so on and so forth. So here you go. So these are all the paths at any one point in time. The amount of trajectories that you see depends on the time. Sometimes you have aircraft that doing go around Palo Alto Airport, for example. So this is all being captured by some ADS-B antennas that I'll show you in a moment. And then, you know, at the middle of the day, so it's about 6 p.m. now, or almost, you have a whole bunch of departures. You start having Pacific departures in the evening, so on and so forth. Every one of those flights creates noise events, right? So how do we measure noise? Typically, this is measured in dBdNL. It's a noise measure, integrated noise measure over a 24-hour period. DNL stands for day-night level. I'll talk about that. And you can do contour maps of where the day-night level is highest in red and where it's lowest in blue, right? And there's regulation in the United States that says if you are exposed to 65 dBdNL or higher, the US government will reimburse you for insulating your house, changing the windows, et cetera, at the tune of anywhere between $1 and $3 billion a year spent in insulating noise from people, just from where the boundary of 65 dBdNL is, the red pin here, which if you were to change, remember that for later on, it could have tremendous economic impact, right? So, but you could say, okay, dBdNL is not the right metric. Maybe I can worry about how many airplanes fly above my head. So these are counts. Right now, we're looking at impact, and we're focusing on metrics that say how many aircraft fly above me that are producing noise events of a certain magnitude or higher. So N above 60 is a metric that says how many events or how many aircraft fly above my head anywhere in the map that have 60 dB sort of noise events or higher, right? So these are various different ways of measuring noise, but this is really hard. So predicting noise, I hope I convinced you, is pretty hard. This is the mumbo jumbo of everything that's going on, lots of different metrics. They don't all relate to the same impacts. So annoyance is one of the impacts, but lack of sleep or sleep interruptions, children not learning, you know, sort of cardiovascular health. There are all kinds of public health studies on these various different impacts. You know, I think it's just a very difficult thing. And finding the metrics that measure what we want to measure is always the hardest thing. All right, a little bit more of Noise 101 so I can set up the problem, and then I'll go into the specifics of the research. So let's say, even though you saw that, what was it, a 1912 or so sort of editorial, everybody complaining about noise, arguably noise of aircraft has been one of the success stories in terms of minimizing environmental impact of aviation. Why? In this plot, you see from 1970, we can't read the numbers from back, to 2025 with a pandemic in between. So let's be careful of that. You see in blue the number of what are called enplanements. So how many passengers are actually flown in the US on any one given year. And you can see that, so it's in millions, so 200 million all the way to about 935 million. So a factor of 4 plus increase in traffic between 1970 and 2020. And at the same time, the number of people in the US impacted, so this is in millions as well, by 65 dBdNL or higher has gone from 7 million people all the way down to about 400,000 people. So you say, why is there a problem, right? So we've quadrupled the traffic in the US, and at the same time, we've decreased by almost a factor of 15 the amount of people that are exposed to what's objectionable noise. So hold that thought too. I'll come back to talk about this later on, but what you will see is that many people, or society has been much less sensitive to noise than we were before. And you will see also that while in the past, most of these people were concentrated around areas of airports, now those areas have spread a lot. You'll see. Why is that? As I mentioned before, you know, what ends up happening, just like in the drawing that you saw, this is Boston Logan Airport, you can see these red lines. They're not individual lines. They're accumulation of many trajectories that are now far more concentrated. So you would argue that before we were spreading the wealth of the impacts of noise, now there are some people who used to have 10 flights a day flying over their heads that now have like 300 flights a day, and they're exposed to a much higher noise level. So, you know, the response to noise of human beings is not a linear function. So if you double the amount of noise, you don't get double the impact. It's a very normal function in some senses. So that GPS in the cockpit, you know, the technology you have in your cell phones, is something that has allowed us to be much more precise in terms of how we route aircraft, plus or minus 5 meters, essentially. And that has concentrated things. So to the point that the complaint locations, which are these blue dots that you see here, and one of the studies that were done around Boston, are very much concentrated around those areas. Okay, so we measure noise by looking at a time event. So the airplane starts being heard, flies overhead, and you hear the maximum noise, and then it goes farther away, and there's a Doppler shift and various other things, but you are radiated by sound energy at various different frequencies, and we put together some different measures. So in here you'll see, the signal itself. You could say a metric is the maximum noise in the entire sort of event that has happened. It takes about 90 seconds for that sort of noise to be heard and for the noise to disappear at typical altitudes or airspeeds. You could integrate the noise before and after a certain amount and sort of measure the total amount of noise in there. You could do some equivalent noise levels at different points. And then for each of the events, you could do metrics that aggregate many events throughout a day. So if you live in the approach path to San Francisco Airport, you probably see anywhere between 300 and 500 of these events a day, right? So the most important one that I'll direct your attention to again is the DVDNL, day-night level, which essentially is an aggregate of all the events throughout the day with a penalty between, I believe it's 10 p.m. and 6 a.m. or 7 a.m. of an extra 10 dB penalty to sort of signify that the ambient noise level is slower, and therefore it's more annoying to have the exact same airplane fly over your house at 2 a.m. than it is to do it at 11 a.m. or something. So this is the regulatory metric. So when we talk about metrics, we'll talk mostly about DNL because that's what matters in the US, at least today. So, all right, last little bit. Unfortunately, this DNL metric that has been enshrined in regulation since the 1970s is actually a really bad metric because you could have 65 dB DNL with a single aircraft event flying overhead at, 114 dB. Or you could also measure this cumulative level of 65 dB DNL with 100 events that are each 94.4 dB. So I will ask you to raise your hand if you think this is more annoying than one single event sort of passing by. So who thinks it's more annoying to have 100 airplanes at 94 dB than having a single airplane at 114 dB, which is significantly louder, but it's one event only. So raise your hand if you think yes. Who thinks it's the one event that's more annoying? So few of you. So yeah, most people think that that this is most annoying, and the DVDNL metric is blind to the frequency magnitude sort of additions. And of course, decibels are, I should have said this, are nonlinear scales. So the addition of multiple events, if you have an 80 dB event and you add another 80 dB event, it's not 160 dB, it just goes up by 3. Okay, so last, in the 1970s, people needed to set a threshold. Is it 55? It's a 65? It's a 75 dB DNL. So what did they do? They actually did some very serious studies of population exposed to aircraft noise at different noise levels. And they came up with what's called a Schultz curve after the person who actually sort of did most of these studies. And what ends up happening is that you have in the vertical axis the number of or percentage of people annoyed, highly annoyed, I should say, versus the dB DNL level. So at 50 dB DNL, almost nobody was annoyed. At about 75 dB DNL, you're at about 35%. And they said at 65 dB DNL, it appears that 10% of the population is highly annoyed. And the powers that be make the decision that that's the reasonable threshold, to actually remedy the situation versus doing nothing about it. That was the 1970s. In fact, the studies were conducted in the mid-60s, right? In 2020, the FAA, they didn't know what they were getting into, decided to redo these studies, and they actually came up with a different curve. And if I superimpose the Schultz curve with that curve, what you see is that we've become a much less noise-tolerant society. So, at 65 dB DNL, whereas the Schultz curve upon which regulations are based said that about 10% of the population were annoyed, and here you had anywhere, on average, that's the mean, and this is the variation over 17 different airports in the US, you're about 65% of the people annoyed, and as high as 85, as low as, something around 45% or so. So things have changed. DNL 65 dB is probably not an appropriate threshold today, but I'm going to skip to this. I'm not done. Okay, so with that sort of introductory discussion, let me actually talk about what I want to discuss today here. So we see that noise is important. We see that it's measured in various different ways, but we don't know if these are the best ways to measure noise, and we also don't know if the tools that we use to estimate what's going to happen when we run out of traffic are accurate enough or not. So in here, I want to present the MONA system. I don't come up with these things, the students do. MONA is the Metroplex Overflight Noise Analysis. So we spent 2 lab meetings sort of trying to figure out what the name was going to be. But it's a system which is the largest data acquisition system for aircraft trajectories and noise in a geographical area that covers almost the entire Bay Area. So about 50 noise monitoring stations and multiple ADSV antennas to capture every flight of every aircraft and every noise impact. So I want to show you how we did that. I want to discuss the prediction methods that are currently used in the US in order to estimate noise from rerouting airplanes around. And I want to use the data that we have, that we presented in this Journal of the American Aeroacoustical Society paper. I want to actually do a validation verification of those tools to see how accurate they are and whether they're sufficiently accurate or not. Of course, our intent as scientists and engineers is to identify issues, to get data that is incontrovertible, and then suggest improvements to the status quo. So if I get time, I'll go to that. So let me start with the MONA system. Metroplex, overflight noise analysis, as you see there. It's a very simple architecture. So we started with about 6 ADSV antennas. ADSV antennas are constantly receiving what is called ADSV out. Every flight management system of every aircraft, once per second, is broadcasting its position, its velocity, some other elements of the aircraft, and an identifier, right? We've also built a bunch, I think we operate about 10 of them ourselves, noise monitoring stations that are all over the Bay Area. And we have access to about 50 more that are operated by San Francisco Airport, which are kind enough to share in real time the data that is actually happening. We built the entire simulation, cloud computing, storage, data analysis sort of capability. And then, we've played around with noise prediction methods from those trajectories, but we can compare now the trajectories and the predictions to the actual noise. So it's a direct comparison between a prediction and a measurement that we actually do. And this system operates 24/7 and has been operating 24/7 for about 6.5 years now. So the amount of data we have is tremendous because on a yearly basis, on a daily basis, you see about 5,000 to 6,000 flights. So multiply by 365 days, and so you can do the math very quickly. But we're at the point where now we have millions of data points, where most of the studies that actually get done for aviation noise have 10, 20, 30 aircraft flights or something. So this is massive, large-scale data from which we argue, you can draw statistical conclusions, right? So this is the thing. It's okay if we don't, some of the data is corrupted or this or that, although we try to do it as well as we possibly can, but we can draw statistical conclusions from, aircraft noise, different aircraft types. If you have about 1 million flights a year, you can say how many 737s do I have, how many Airbus A380s, so on and so forth. So we have all that data here. These are the noise monitoring stations. I'm a computational person, but we built these things. They have little computers in there. They communicate through Wi-Fi. We put it on roofs of friends and family in our buildings and various different universities around the Bay Area, and we measure the noise. We get all the noise traces. We do a lot of post-processing, and then, of course, we sort of find impacts. By the way, I always put this one up because we started taking data before the pandemic. So this is what happened in the Bay Area. Different airports. That's March 10th, 2020. So the traffic decreased by about 80 to 85%, depending on the airport in the Bay Area. And the noise complaints went down by 80 to 85% as well. But I'll tell you more about this. So a little bit more about the system, because we actually spent like 3 years building the system. It sounds simple, but you have to take all the data, post-process, automatically do it, throw out outliers. Sometimes the Raspberry Pis and these things fail, and you have to get up in the roof and sort of restart it. So we started getting more clever about these kinds of things. So it was a labor of love, mostly done by undergraduate and some master students at Stanford, right? And the software developer that I talked about. So here, MONA stations, sort of done all over the place. That's the example of what we do. you know, the ADSB messages, the raw audio being recorded, you know, everything being sent through a very sophisticated sort of software engineering infrastructure to a massive database in the cloud. And the database keeps adding all of these things. There's some schemas for the database. So now you can query for individual flights or aggregate flights over any period of time, or every types of altitudes, anything that you want. So very easily queryable database. And again, the data set keeps increasing and increasing and increasing over time, because it's important to see many different types of airplanes at many different weather conditions during different seasons, so on and so forth. So you have a really comprehensive data set. So that's what the system does. We also had to not just collect the data, but also once we see a trajectory of an airplane, we actually predict the noise that trajectory, and we do this in real time. It's going to the noise that it's going to generate at various different stations where we actually have noise monitoring stations. So we run a whole bunch of analysis through this AEDT program that I'll mention in a moment that FAA has. And for that, we feed the trajectory, the aircraft type, the engine type. You know, if you have the altitude and you have the airspeed, you know, you can back out the throttle settings. So we're virtually flying each of these airplanes and doing the analysis to sort of come up with the noise prediction according to the FAA mandated tools. And, you know, there's a lot of database stuff. We run about 128 instances in the cloud in parallel, so we can process all of the flights of the day essentially in real time. So it's not super complicated, but you know, in order to process an entire year of flights, which we do repeatedly in order to do various different studies, you actually have to spend probably about 3, 4, or 5 days of computing with 128 instances of this. And then, you know, it produces all the data. I won't sort of belabor the point, but we had some really good computer science students who helped us automate all these things in order to make sure that it's pretty much hands-off right now. So, you could analyze the noise of an aircraft in various different ways. So let's say you have a model of the airplane. I do computational fluid dynamics, external aerodynamics. I could do a transient simulation of that aircraft, that individual aircraft, a large AD simulation, if that means anything to you. I could look at the energy radiated. I could do aeroacoustic models, and I'll spend, you know, 5 weeks doing a single flight, so I cannot possibly afford that. So we have different types of acoustics models for aircraft, and AEDT is again the regulatory approved noise model. We want to see how well AEDT predicted the noise that we've been measuring with the MONA system. So AEDT, you know, it's actually relatively simple. So if you have an observer location, let's say you put a microphone on the ground, and you have an airplane that starts flying along that flight path, you know, as it goes by, the noise monitor or the microphone at this location is going to collect the signal, the noise signal. And from there, you can just come up with a particular measure or metric of noise. In particular, we're going to look at various different dBDNLs and max metrics and picola metrics. So we do this 24/7, 365. It's operating continuously. That's require a little babying every now and then when something shuts down. But in general, it's a fully automated system at the moment. By the way, we're open sourcing this because there are about 7 or 8 airports around the world, or communities around airports around the world that want to install a very similar system, both in the US and in Europe. So then we correlate. After we predicted the noise, we have the prediction of the noise from AEDT, we have the actual data, and you know, we just sort of draw conclusions. And this is just a simple illustration of 2 noise events where we're looking at SLM, the sound level monitoring stations. These are the physical microphones. So this is experimental data, and AEDT, those are the predictions. And sometimes it does okay, sometimes it doesn't. When you look at 1 or 2 or 3 or 10 flights, it's actually pretty hard to sort of see anything. What you see very quickly is that the microphones in orange and the predictions, you know, they may have similar maximum values, but the breadth is very different. The atmospheric distortions due to turbulence and sort of winds and gradients of the atmosphere are very different. And effectively, when you start accumulating not 1 flight, but 1,000 flights, 10,000 flights, 100,000 flights, you see pictures emerge very clearly. So let me actually tell you a little about what we got out of these sort of the data sets, et cetera, et cetera. So I'm going to just, let's see, what do I need to tell you about this one? I'm going to just give you sort of the high level details. So our main objective, and this is what the FAA funded us for, they knew that AEDT had lack of predictive capability, especially further away from the airports where the noise levels are a little lower. Still 55 dB, but or 50 dB. They knew that maybe the predictions will be a little bit better in really high noise environments close to the airport. So, but they didn't have enough data to actually look at this. So the initial grant was to actually provide to them an assessment of the accuracy of the tool that they rely on day in and day out. So we took a full 12-month period. So I think this is July 21 to July 22, essentially, although we've repeated this many times. We look at every flight, every microphone location, and we provided to them an entire detailed assessment of how good or bad the predictions actually were. So I'm going to show you this. This paper down here details the measurement system, so the infrastructure, but the Jessup paper is the one that details the results. It is, we think at least, and nobody has come up to say otherwise, the first use of very large scale data in aviation noise studies and estimations and impact assessments. So because there's so much data, I'm going to focus on 2 points. If you see here, this is KSFO, so that's the entire set of flights. These are the arrival flights into SFO over a 24-hour period, right? So that's SFO. There are planes coming from Europe that fly and go over the bay, turn around and come for a landing. All the planes from the East Coast from around this, this is called Bodega. The flight control people give these paths in the sky, these funny names. So Bodega, because it passes by Bodega Bay, there's a waypoint there. The ones that come from the East Coast, it's called Diamond. The ones that come from San Diego, for example, Southern California, Mexico, South America, it's called Surfer, SERFER, it's that path there. And then Pirate is the one that typically comes from the Pacific. So there are all these approach paths that are coming there. I'm going to show you results at 2 locations. So I'm pointing at the one that we call NMT, Noise Monitoring Terminal 12. So SFO, that's the landing path. This is about, what do I say there? A few miles, like 5 miles, 6.5 miles, sorry, before the touchdown. The aircraft are about 1,700 feet of altitude in there, and they're following a very, 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 very tight path. They're in final approach to San Francisco, very small deviations in altitude or, latitude, longitude. And then I'm going to go right next to my house. So the side-by waypoint, by the way, this is almost a 57 dBDNL area. So where the noise of the aircraft sort of blends a little bit more with the background noise. This is relatively quiet. So we wanted to assess at multiple locations. In this case, a louder location with lots of aircraft and concentration. In here, a quieter location in Palo Alto, California, right? So let me actually get to the modeling a little bit. So how do I predict the noise? I take the trajectory of the aircraft and I take the exact aircraft type and engine. How do we do that, by the way? We have to have models of what throttle setting you have to have in order to fly a particular trajectory. So we invert all that, and I won't speak about these kinds of things, but it's all in there. It uses a model from Eurocontrol called BADA, VADA, or Base of Aircraft Data, which is actually based on certification data for all of the aircraft. So it's extremely accurate from thrust, throttle settings, fuel flow, so on and so forth. And for regulatory purposes, you don't even have to follow the real trajectories of the aircraft. You have to follow the latitude, longitude path, and then they have these sort of standard profiles, which obviously pass over these microphone stations at different altitudes and don't produce good predictions of noise. So we try with both methods, following the exact trajectories of the aircraft versus following these sort of standard profiles. So if you are curious as to what this looks like in terms of mix of airplanes, this is 100% in that entire year of data of the aircraft types that fly into the San Francisco airport. And if I go here, I can point at it. It's a bunch of Embraer 175s. It's a bunch of 737-800s, Airbus A320s, 737-900s, Airbus A321s. So between, and other 737 types, between regional jets and single aisle aircraft, Airbus A320 and sort of Boeing 737 family, it's the lion's share of aircraft. It's about 3/4 into San Francisco Airport, which is a major international airport. But you also have 767, 787s, Airbus, even smaller aircraft, 787s, Airbus A350s, some Airbus A380s. So you have all kinds, but that's the percentage distribution. And we have about 500,000 flights into that we deem reasonable into SFO with that distribution. Oops. The first thing you will actually see, if I go down here, is this histogram of the measured noise. These are counts at different noise levels. And sorry, you can probably see it from there. This is 79 dB, 70 dB, 60 dB, right? So the actual measurements at this one microphone location have a distribution of flights over an entire year that looks like that. The actual predictions have a very different distribution. So it's peakier because, you know, the same aircraft produces the same noise all the time if it flies in the same conditions. Whereas, you know, in the atmosphere mixing and the different weights of the aircraft and various other things, there is a much sort of smoother profile. So that tells you or gives you the first hint that something's not really working very well. So let's see. We have to be very careful to make sure that the noise we measure and that we compare to predictions is noise measured only from aircraft and not the dog going by a microphone and barking, or somebody with a jackhammer, or a truck going by, or, you know, something else that is actually producing noise. And this is actually more difficult than you think it is. But if you have the data and you automate these systems, it can actually be done. So midnight to midnight, single microphone station, you record the noise over 24 hours, you know, once per second. This is sort of the frequency that we sort of record stuff. This is what happens. You know, there's a noise that has a varying sort of base or lower value. There are lots of noise events that are those peaks. You know, they tend to be relatively large. Let's focus on a little area here between 7 p.m. and let's say maybe 11 p.m. or so. So these are the types of noise events. So what's a dog barking and what's an airplane? Well, remember, we have ADSB data, so we know exactly where every airplane is at any moment in time, and we have time-stamped noise traces from the microphone. So I can definitely go ahead and do some signal filtering. I can go ahead and find out what a threshold noise level is, and I can exclude peaks that are between, you know, the threshold and plus or minus, I think, 5 dB. And then eventually, I get only some candidate noise events that may have been created by aircraft. And to have the highest quality data for these statistically significant comparisons, what we do is we say, oh, okay, let's look at airplanes that were flying around, and let's find out how many of those peaks had an airplane flying by at that particular point. And, you know, we do this, we identify them, we find all the specific peaks, and that's how we do everything. Not only that, but once we have a peak that we know happened at the exact same time that there was an airplane flying around, we now create a function that should be the profile with some parameters of the noise event. It's called a Lorentzian, if you've ever heard these things. So we fit the Lorentzian with the actual data, and we reject any event that doesn't have a goodness of fit, as measured by the L2 norm of the difference between the Lorentzian with the appropriate parameters in the aircraft noise. So that does not have a goodness of fit of more than 70%. So, you know, even though we're pretty confident this was an airplane, it's maybe complicated by other noise events that happened. We throw that away, but that's an airplane, that's an airplane, that's an airplane, that's an airplane. And we only keep in the data set that we do comparisons on things that we are absolutely certain correspond to aircraft overflights and only aircraft overflight. We even throw events when there are two aircraft flying by and their peaks are close to each other, so on and so forth. So it's not only the largest data set, but it's the highest quality data set. And we spent about 1.5 years perfecting these types of algorithms. So, okay, so let's look at the microphone that is a little bit closer. According to the FAA, this is where the AEDT noise models are going to shine. They were made for, you know, low altitude, relatively high noise environments, et cetera, et cetera. We take a whole bunch of flights, we throw away many different things, but eventually we have about 100,000 flights that we do the predictions for. You know, again, you know, lots of aircraft flying at the same altitude, same airspeed, you know, and relatively low altitude, so relatively high noise, right? So when we look at what's actually happening there, and then we look also at this quieter area, it's a very different area, where we also keep about, you know, 90,000 flights or something. What ends up happening is what you will see next. This is kind of what they say, this is the money plot. So let me explain it and you can understand. So in the horizontal axis, well, every purple dot in this graph is one flight over that 12-month period, so a whole year. So every one of those things at one microphone location represents one overflight. In the horizontal axis, I'm plotting the measurement of noise in decibels from that noise event. So the x coordinate of, let's say, that point, it's the noise about 82 dB or 81 dB that was actually measured for that event. In the vertical axis, I have the predicted noise intensity from AEDT, from the model that's in that particular tool. So obviously, if we had perfect prediction of every noise event, every one of those purple dots will be along the diagonal, correct? Same measure as it is predicted. Of course, there's quite a bit of spread. So in fact, it's a stratified set of plots where the actual measured, let's say for each aircraft type, so each of those strata that you see there correspond to different aircraft types that have been sort of labeled and that have centroid that is also sort of created in there. What you're not seeing, for example, Airbus A320s right here. In the actual measure system, the same type of aircraft produces different amount of noise at different points in time. The reason being that we don't know the exact weight of the aircraft, how much fuel is left, how many passengers are on the airplane, so on and so forth. You don't know the state of the high lift system. You don't know the actual landing gear has been deployed or not, although we have an idea that, at this microphone location, all the landing gears were deployed, et cetera, et cetera. And you see that the prediction is not broad enough. It's actually really tight and concentrated. So the model inside of the program does not take into account this variability, and in fact sort of predicts that the same aircraft type predicts pretty much the same aircraft noise, if it's flying at the same altitude and airspeed in some senses. So notice also the centroids, the red dots of all of the aircraft types that we have here fall under the diagonal. That means the predicted noise is lower than the actual measured noise. That means the methodology we use for prediction is under predicting, not over predicting, except for the 727-200s, of which there are about 20 of them or so a year or something. But the vast majority of the aircraft, particularly the ones that fly in extremely large numbers, are always below the diagonal. So huge under prediction of noise. And I'm going to quantify that under prediction of noise. So the regulatory tools that we have today estimate noise to be significantly lower than the actual noise that we measure. So this is the first time that that type of study is actually done for arrivals. And it's, well, I have lots of histograms. You can see the concentration in the histograms of different aircraft types, so on and so forth. The interesting thing is that at that microphone location, and I'll show you at the other microphone location, AEDT underpredicts anywhere between 2.5 to 3.5 dB. And if you're not in acoustics, this may sound like, well, is that a big number? Is that a small number? So if I have two identical 787 airplanes, let's say, identical airplanes running at the identical conditions, same throttle setting, and I measure the noise, I'll measure some amount of dB. If I take away one airplane, how many fewer dB? Those of you who know what a dB is, that's all this. We go down by 3 dB, right? So 2 airplanes produce a certain amount of noise. I take one airplane away, 3 dB. These tools that we're using for regulatory predictions have errors of 3 dB or larger. So they're effectively not distinguishing between 1 or 2 airplanes of the same kind. That's a massive number. It's also more massive, and I don't have it in here because regulation, so US law, says that if people are going to reroute people, the FAA, are going to reroute the flights around, the San Diego area, if you're in a 55 dB area or lower, you're not allowed to change the route of the traffic if it's going to create a noise impact of more than 3 dB. And what we're telling you here is that the predictive capability is barely able to actually sort of meet the requirements of that typical variation. Yet, we do all these environmental studies and people check all these things, and there's no guarantee that the predictions are actually going to do what is going to happen when the changes happen. Sorry. Now, the FAA will also highly believe, and I, as a mathematician or part-time mathematician, I believe this. They say like, yeah, we cannot predict individual flights, but on aggregate, trust us, we do much better in the predictions. I'm like, well, if every aircraft we predict underpredicts, the average is not going to sort of wash out. So if you had some above and some below, yes, I could buy that, but in general, no. And in fact, when we do not just one single flight, like you saw there, but we look at aggregate measures like DNL, what you end up seeing is, sorry, this is the next graph, so I'll show you here. What you end up seeing is that the DNL level is actually also underpredicted by about the same amount. So that's the current status quo of where we're at, and we hope to do a little bit better. So Two more slides. I promise I'm going to skip some things because I want to leave time for Q&A. But the models themselves are based on some statistical correlations of noise created by the engine, by the airframe, et cetera, et cetera. They were created in a time in the 1970s and 80s, and some modifications in the 90s, where the source of noise that dominated for aircraft noise was the engine noise. On approach to SFO, that is no longer true. The engines with high bypass ratio, lower fan pressure ratios, et cetera, have been such that the engine noise is not the dominant source of noise, it's the airframe noise. And in fact, what we do is we look at SLM. So this is the measured noise in one measure of noise. So what you see is all those blue dots, they're actual measured noise, plug versus calibrated airspeed. So how fast the airplane is flying. As you can see, the slope of that line is such that as you go towards the right and you go at higher airspeed, you expect higher noise. If you look at the AEDT predictions, which are these orange dots, actually the physical model is incorrect in the sense that as the average calibrated airspeed of the aircraft increases, the noise goes down because it's mostly an engine noise model that sort of has some weird interactions with the speed. And this is a different metric, but the same thing. So the physics of the model is not sufficiently good for the current aircraft types that we have today. We must do something about it. Let me actually, I think I've given you all these things, but so first large study of arrivals and departures, we've only presented arrivals here into any sort of airport in the world. Statistically significant proof that we are underestimating, the noise by a very significant amount, and there's some elements in the physics of the models that are just pure. We have to do better, right? So the possible predictions is you must improve the noise models in these predictive tools, or understand that this is an imperfect model, and we have to factor the uncertainties of the model in the regulatory environment that allows us to reroute aircraft or not. The last thing that I would say is, well, let me try to skip through this. What I would say is that if you have a lot of data, we keep accumulating data for every aircraft type under every atmospheric condition at any time of the year. Well, the obvious thing is to say, it's like, hey, the hell with the actual physics. Why don't I create a model that is just purely data driven? I don't advocate this, but it actually works. So, but it's purely data driven. So why don't we create a model for every aircraft type that actually is trained on the data that we've actually acquired for each aircraft type? So we had an undergraduate who's now doing a PhD, but we had an undergraduate sort of take all this data and build a Gaussian mixture model that tried to fit the data seen and the distribution of the data that is seen. And I'll just leave you with this thing. This is the standard, sort of the predicted versus measured. I don't say it here, but I can say it to you guys that this is Boeing 737-800. So a very typical airplane. All the dots under the diagonal, the plus or minus 5% sort of error lines are in that blue area. That's the typical sort of status quo of what we have now for one aircraft type only. If you actually do a very simple pie chart, the training model that an undergraduate can do, this is what you actually see. So we've matched the value, we've matched the prediction, and what you end up having, actually, we've matched the distribution that we observed in various different events, because there are a lot of parameters that we do not know directly. And we can actually get to models that work relatively well for these things. So we're pursuing this for lots of different aircraft types. It's a combinatorial problem. It's an aircraft engine combination. There are hundreds and thousands of combinations that AEDT has, but we're just showing that this is possible, and we should be able to do better, to the point that the average error of these simple models, and they can be improved further, is about 0.25 to 0.4 dB, which is somewhere where we should be. So anyway, I'm going to pause there. You can read the papers if you're more interested in this thing, but we think that the body of evidence is incontrovertible. You can now sort of understand and assess the shortcomings of our prediction tools. If we want to continue to grow the traffic in the US, and it does grow at about 3% per year over time, while minimizing those impacts, we have to have better tools in order to do better rerouting. Of course, I mentioned this at the beginning, but we have to start thinking about what metrics we're going to use to measure the impacts. And there's a whole lot of other work that I haven't talked about that goes on in the project in that particular area. And then, finally, this is a complicated problem. Everybody complains about noise. You have to talk and inform people because the air transportation system brings tremendous benefits to the communities. And we can't just say, hey, I want to have my Amazon package delivered to me tomorrow with my laptop coming from China. And at the same time, I don't want any aircraft noise. So I think it's really important. And I've been in many San Francisco airport roundtables to explain to the community, that there is a penalty, obviously, the noise that they don't like, but at the same time, they're getting a lot of benefits. So with that, I think I'll just sort of pause there and leave both the disclaimer that the FAA tells me to put. These are my opinions, not those of the FAA, and also a copy of the paper that we presented with these results last year. So thank you very much for it. I'm happy to take questions if anybody has questions, but
Yeah,
I know it's gone a little bit longer than I was planning to. Yes.
Oh, well, lots of questions, but one thing that I wanted to know, are you guys maybe extending this to drones flying over?
So a lot of people complain about drones.
Yeah.
We actually, a lot of things fly in the Bay Area. We excluded general aviation aircraft, we excluded any other event, so we were focusing on the ADSB data, so we focused the effort mostly on commercial aviation. So no, we have not been doing drones, although the FAA through the Ascent Center of Excellence has a number of programs in order to characterize the annoyance of noise from drones, which tend to be in the higher frequency range where the human ear is fundamentally more annoying than the dBA and C scale. So, well, although I have to tell you, I don't know if you like drones or not. I'm agnostic here. There are a bunch of companies that are trying to do drone delivery. One of them is called Wing. It's either Google or Alphabet. And one of the very clever things they're doing, if you are interested in physics of propellers, is they have four-bladed propellers where two of the propellers are longer than the ones in the other side. So they actually create tip vortices that are of different intensity, and they roll up together, and they end up halving or cutting in half the frequency of the noise in order to have the same noise sound power radiated, but at the same time having much less annoying noise. So people are spending a tremendous amount of time on that, in EV tolls and various other things in order to mess around with the acoustics of each of these components. Yeah. Question.
You mentioned about building the empirical model that kind of gives a better fit. Is there any effort on improving the physics-based models based on this data?
Yeah, so that's a purely data-driven, based on experiments model, and it works pretty well. But NASA has been working on a step above what AEDT predicts for noise called ANOP, A-N-O-P-P, and particularly ANOP2, which look at different components and how they combine, et cetera, et cetera. So we've done predictions with ANOP2 instead of with AEDT, and they still are about a 1.5 dB off, and it takes a long time to construct one of the models. But I mentioned I'm not an advocate of just doing data-driven purely. We have the data. I think we should have models that are not perfect, and we should be actually trying to fit discrepancy models based on the data-driven and the true distributions in order to get something that is both physics-based and sort of data informed. So we're trying this at the moment. But of course, if you have to do analysis of 100,000 flights, you cannot spend even an hour of compute time doing each of the flights, because then it's just a tremendous budget. So you're forced to use these simpler models, and I think this is one of the areas where data-driven plus some improved physics is pretty nice.
Another question.
Yeah.
So when you look at route histogram, that would look like Maxwellian.
Yes.
You expect.
Yes.
Now.
Well, yes, you expect some distribution of noise for the same aircraft type, right?
Right.
Yeah.
So have you thought of working with those distributions instead of working with the data?
So the data-driven models have distribution, and again, the reason that two 737s flying over at the same altitude, same airspeed over this point may produce different noise is related to many things, right? One is the weight of the aircraft, which affects the lift, affects the thrust, and everything else may be very different. One of those 737s may come from Washington, D.C., the other one from San Diego, the fuel load may be different. So weight variations, which you cannot infer by just looking at the airplane in the sky, can actually have variations to state of the system, atmospheric conditions. So there's always going to be some natural distribution of noise, even for one same aircraft type under the same conditions. The data-driven models can match not just the value, but also the distribution. So that's why I mentioned that that's it's, so, you know, sometimes people like me would like to measure everything perfectly, but we can't. So you have to put up with the fact that the predictive noise models have to have sort of a probabilistic element to them, or some distributions that are, you know, informed by what we observe in reality. Thanks for the question.
I was just curious, you mentioned the word simulations a few times when you were giving the
yes.
talk, so I was curious whether you've actually used some of your high fidelity models at all,
We have.
even not even in the research development.
No, well, I mean, there's a lot of literature, right, on sort of aircraft noise prediction. At the full aircraft level, very few, because I mean, this requires really high fidelity, large eddy simulation if you come to capture the frequency content, the broadband noise, the total noise, the separation, the vortices. So people have been trying to do this, but I would say the state of the art is still that you need massive supercomputing equipment to even sort of estimate the noise somewhat accurately. There's been a lot of jet noise, you know, in the community, large eddy simulations. I would say for the last 15 years or so, we're being very, very good of extremely high fidelity simulations, but I think it's still out of scope in terms of being able to do more than one or two aircraft. And then you want them at different conditions, you want them at different altitudes, at different airspeeds and various other things. So that is very challenging. So no, we have not done very high fidelity simulation. We've relied on the very low fidelity. ANOP2 is kind of an intermediate fidelity model. I think that is probably the answer for these types of applications. Of course, if you're Boeing or Airbus and you're trying to certify the aircraft at certain noise levels, you may be able to sort of focus on doing much higher fidelity simulations that look at chevrons and, you know, sort of compliant surfaces in order to minimize noise and various other things. But in general, for anything that's sort of fleet level analysis and thousands of events, it's just prohibitive. So. Yeah, question.
Were flaps considered in computational models?
Yeah, so the airframe noise part that I talked about that is mispredicted completely by those current models, flat noise and flat edge noise is one of the key contributions. So the models there have some parameters that go to the amount of deployment of the high load system, which by the way we don't know, right?
Flaps are usually lower during approach, so
Yes, so you can make some estimates, particularly when you're in final approach. But when you're turning around Palo Alto, you know, we've had actually members of the team take the same aircraft type both times, and different pilots deploy flaps at different locations, et cetera. But in general, there are parameters that go into this. There's also the drag that accompanies the additional lift from the flaps. That ends up changing the thrust setting that you have to have the engine in order to continue to fly that trajectory. So that is accounted for, but at a very simple, well, the thrust is very well accounted for, the flaps at a very simple level. These are parameters taken from its certification video. So very efficient in some senses. Thanks, yeah. Any other questions?
Okay, well, thank you again for coming, everyone, and let's thank you.
That was
Thank you.
That's fine. You thought I